Hey folks, it's Miss Gray again,
And this is Mrs. Uy.
and we're here to work with you on the early periodic tables so that we can understand what scientists thought about the periodic table before
and
how we got what we have.
Yes.
All right, so here's what we knew in the mid-1800s, saying we as if I was around then.
Yeah.
I know I'm old, but I'm not that old.
Oh no, Miss Gray.
So
No,
out of
you're
the
not.
60 different elements, 5 of them
Were identified as gas at room temperature. And
Right.
they're all non-metals, right, Miss Gray?
Right, gases are all nonmetals, and here's the 5 that they knew about: hydrogen, oxygen,
Nitrogen
fluorine, and
and
chlorine.
chlorine.
Those are the ones, the gases they knew of.
All right. And 2 were identified as liquids.
So there's one liquid metal, that would be mercury,
Mercury,
and then another liquid that is a nonmetal,
yes.
bromine.
Bromine.
All right, and then that's only 7 elements out of 60 that they knew. All the rest that they knew of were solids.
All 53 of them
Yeah.
are solids.
Right, and so now our periodic table has like 116 or so elements. Yeah, we know of a lot more than what were identified
In mid-1800s.
mid-1800s. So knowing 60 elements, it was hard to keep track of which one was which and what they all did.
Yes.
We wanted to have a way to organize the elements and learn about them more effectively. So what scientists did at first was to put elements with similar properties near one another,
Near one
in a
another.
little table. Like they made index cards, right?
Yeah, and then
And
write down all those elements.
Wrote down what they knew about all of the elements and things that reacted in similar ways. They got put next to one another.
Yes,
And so one of the first guys to publish his work was Dmitri Mendeleev.
Mendeleev.
Maybe there are other chemists who did this too, but he was the one who published his work
Okay.
in 1869.
1869
So let's have a look at what his periodic table
looks like.
And what I'd like you to see here in this group 1 is that he considered these elements that combine in a 2-to-1 ratio with oxygen as being similar to one another. And so those are things that we know now as alkali metals, lithium here, sodium, potassium.
Potassium.
But then there were also goofy things in there, like copper 1 combines in a 2-to-1 ratio, but copper 2 combines in a 1-to-1 ratio.
1-to-1 ratio.
Right? So some things didn't stay in there the whole time.
Okay.
Right? Group 2 reacted with oxygen in a 1-to-1 ratio. And then over here you'll see the H. That means how did it react with hydrogen?
Hydrogen.
So carbon reacts with hydrogen to make methane, CH4, right? And
CH4.
all of the other elements in this list did the same way, reacting with hydrogen and reacting with oxygen. It was 1 to 2.
1 to 2.
Like CO2, carbon dioxide.
Yes.
Right? So they tried to group them by similarity, not just in getting bigger in size as you go from top to bottom,
top to bottom.
but also grouped by how they react with oxygen and hydrogen.
Yes.
So that's how it was organized at first. Let's watch a little clip about it.
Okay.
In 1869, a Russian chemistry professor named Dmitri Mendeleev was writing a textbook for his students when he began to wonder how he could best explain to them the 63 elements that were known at the time. To help formulate his thoughts, he constructed a card for each element. On each card, he wrote the name of the element, its atomic weight, its typical properties, and its similarities to other elements. He then laid the cards out like a game of solitaire and began arranging them over and over, searching for patterns. Then came the moment of discovery. Before him was something extraordinary. The elements fell into 7 vertical groupings. Each periodic grouping had members that resembled one another, both chemically and physically. Mendeleev had discovered the periodic table of the elements, a map showing how all the elements related to one another. A map so precise that Mendeleev believed he could also use it to predict the existence and properties of 3 elements no one had yet discovered. One would be like boron, he said, one like aluminum, and one like silicon. Eventually, the elements were discovered, and Mendeleev was proven right.
You see it.
Why is the periodic table of elements significant? It forever changed the way that everyone would learn and understand the elements. The periodic table of elements is to chemistry as notes of music are to a Beethoven sonata. In honor of Mendeleev, his name is now literally attached to the periodic table. The element 101 was named after him. It's called Mendeleev.
So that's the story of Dmitri Mendeleev.
And the periodic table.
Right. So we mentioned before, he put them in order by size, and by that we mean by atomic weight.
Atomic weight.
And then he used another category to classify them into the families, the ones that go up and down, and he called it combining capacity.
And by that we mean
Chemical properties.
chemical properties.
Right? How it reacted with oxygen or hydrogen. Now today's periodic table is arranged in a slightly different way.
Okay.
Instead of atomic weight, what do we use?
They use atomic number, right?
The atomic number tells us the number of protons in the atom, right? And
The number of valence electrons.
the number of valency electrons helps us distinguish its chemical properties. So it's still using combining capacity.
Yeah.
Only we can be more precise and say, you know, these all have only one valency
Valence
electron.
electrons.
And the scientist who came up with this new arrangement was Henry Moseley.
Mostly.
He's the dude that discovered protons and connected that to atomic number. So why would we use atomic number instead of atomic weight?
Atomic weight.
Well, we got 2 good reasons. Because atomic weight doesn't always put things in the right order.
Example.
Cobalt is heavier than nickel.
Then nickel.
And what's the number for cobalt?
It's 27.
Its number is 27, and
then
nickel is number
number
28. So even though there's more protons
Yeah,
in nickel,
in nickel.
there's more neutrons in cobalt, and that made it heavier.
Okay.
And so when we put them in order of atomic weight, we got them out of order
Yeah.
for the number of protons.
Exactly.
And then here's another good reason. Some large atoms have lots of different types of isotopes. For instance, chlorine
Chlorine,
has 35, and then we have
yes.
chlorine 36.
36.
So that would always be for chlorine 17 protons, right?
Yes.
No matter what.
Mm-hmm.
And 17 protons. But how many neutrons?
Neutrons.
To get a total of 35, we need 18 neutrons for chlorine 35. Agreed? That adds up to
Yes,
35? Okay, good. My
35.
math is okay today. And then for chlorine 36,
You need 19.
we need 19
Yeah.
neutrons. And these two happen to be almost equally abundant. So the mass of chlorine atoms is considered 35.45
453
because your
to be
chance of
exact.
having chlorine 36 is almost the same as your chance of getting chlorine 35.
Yes.
So as the atoms get bigger, the weight is less reliable.